Hello everybody and welcome back to Chem Talk, where today we'll be talking about free energy and equilibrium. So in a previous video we have already covered free energy, but just for the sake of seeing how free energy and equilibrium really relate to each other, we're going to go over free energy again. So what is free energy? Free energy is the amount of energy available in a system to do the work of a reaction. And there's a specific equation that we must follow in order to find the energy required for a reaction to occur, which is delta G equals delta H minus T delta S. And all of these can have standardization, or, it also just depends on whether or not the other factors are not standardized. Standardization just means that there is a specific value that you should be following, and usually these values are found out of the back of your textbook or something like that, or they're usually provided to you. So delta G is our Gibbs free energy, or as I will be referring to it today, free energy. Delta H is our change in enthalpy, and T delta S is the portion where temperature in Kelvin is multiplied by our change in entropy. So when delta G is positive, or when the value is above 0, the reaction favors the formation of the products, and heat is actually a product of our reaction. If delta G is negative, or the value is below 0, the reaction favors the formation of reactants, and external energy must be applied in order for the reaction to occur forwards. This is where heat is actually a reactant, and it must be applied in order for the reaction to go forward, or else the reaction will actually go backwards, or in the reverse way. Now, on the flip side, what is equilibrium? So equilibrium is when the equation or the reaction that you're doing is at equilibrium. That means that the concentration of the products is the same as the concentration of your reactants. This does not mean that your reaction has stopped. Your reaction is still going on, but it is at a point where it's continuously going back at the same rate as it is going forward. So as you can see on the screen right here, we can see that the equilibriums A and B are our reactants, and C and D are our products. So the reaction is occurring simultaneously at the same rate to ensure that both of the sides are at the same concentration. Now, different factors can change our equilibrium, increasing and decreasing our concentrations on both sides. This favorability can actually be measured by our equilibrium constant. As we will see later on, it can be referred to as KEQ, or K equilibrium, Kp, or K in pressure, or Kc, which is K in concentration. So it can be either one of these, and we'll see it written in a different way in a little while. So KEQ is basically our concentration of our products divided by our concentration of our reactants. So just to break down what concentration we're multiplying, you see our regular primary number in front, which is the amount of molecules we have on each side. So you're going to have the concentration of your reactant, and then the exponent is going to be the amount that you have. So basically this is all related to rate, and if you want to check out our video about rate, you're more than welcome to do that. If our equilibrium is below 0, that means that our reactants are formed to be favored. So that means that our reactants are going to be more favorable to be formed rather than our products. If the KEQ, or our constant equilibrium constant, is above 1 or greater than 1, this means that our products are favored to be formed, and that means that the reaction actually is favored in the equilibrium of the products. In equilibrium, just because the products are favored does not mean that the reactants are not being formed. They're both being formed at the same time, but more reactant is being formed at a higher rate than our reactants. So that means that there's going to be more product concentration present than our reactant concentration. Now, how are these two related? Why should you know the relation between these two? Now, below you're going to see there is a graph, and on the vertical axis, or on our y-axis, we're going to see that it is actually in Gibbs free energy, and our x-axis is the reaction progress. So we see as the reaction occurs and as it goes forward, we can see that our Gibbs free energy is actually decreasing, and this is when our reaction is occurring forward and our delta G is below 0. So we can see that it's decreasing, and right as delta G equals 0, this is where we hit our equilibrium. This is where the concentration of both the products and both the reactants is the same. Now we see that the reverse reaction is going to occur when delta G is actually increasing, it's increasing, and we see that since the value is positive, our reaction is going to be favoring our reactants, which is actually going to be in the reverse reaction. Now, in order to link both delta G and our KEQ together, there is a specific formula. I'm not going to go over the derivation of that, but if you really do want to, you're more than welcome to look that up on our website, because going over the derivation is very complicated, and I just want to focus on how the two are related rather than how we get to this equation. So we can see that delta G is related by negative R, which is our constant. It is 8.34 times 10 to the negative 3 times our temperature in Kelvin. And then this is natural log. So we have our negative RT times natural log of KEQ. So natural log is a algebra term. So if you are unfamiliar with that, go and review that from your textbooks or from your homework or other resources that are provided. Now we can actually switch up this entire equation in order to find KEQ with the same values. So say you have KEQ and you want to find delta G. So we can change this so in order to make it equal KEQ so you can find that value. So KEQ equals E, which is a constant variable, to the power of, so this entire following part of our equation is actually to the power of E. So it is delta G standard divided by negative RT. Now we see that we have the same phrases involved and they're just in a different order, just so we can actually have it equal to different constants that we want to find. Now we can also rearrange this equation if we want to find R, if we want to find T or anything like that, but for the sake of relation and for the sake of this video, we are going to be going over only the derivation of delta G equation as well as the KEQ equation. Now we have a example on the screen right now. So this following equation is 2SO2 gas plus O2 gas is equilibrium with 2SO3 gas. And we know that our temperature is 298 Kelvin, and we want to find the equilibrium constant. Now, I have provided our delta H standard values as well as our delta S standard values, and this comes in handy when we're looking at the following problem. Now, the first step of finding this is that we want to find delta G in order to find our KEQ because of the previous equation that we went over. In order to find delta G, we have to find delta S and delta H in order to plug it into the previous equation that we went over earlier in the video. So on the screen right now, we'll see that delta S is equal to the total S or total entropy of our products minus our entropy of our reactants. And after you use the following values, we're going to be able to see that delta S equals negative 0.188 kilojoules per mole. You want to make sure that both of our values are in the same constant or in the same units. As you can see, the values of delta S actually came in joules per mole, but we had to divide that by 1,000 in order to make sure that it came in kilojoules per mole. Now on the other side, we also have our change in enthalpy. So we see that our total enthalpy of products by our total enthalpy of reactants is equal to negative 197.78 kilojoules per mole. Now we see that we have our following values for delta S and our delta H, and we plug this into our equation that we had earlier. So delta G standard equals delta H standard minus T delta S standard. And after we plug in our values, and we can see that the temperature is involved, so we're going to use the temperature that we were given, it is going to see that we have delta G equals negative 141.756 kilojoules per mole. Depending on significant figures, you can round up to negative 141.76, or if you're doing whole numbers, you would round up to negative 142. Now, we see that our negative value in delta G actually indicates that there is a favorability of a product. So because there's this favorability of products, we want to make sure that our KEQ is a positive value. If it is not a positive value, you're doing something wrong. We want to make sure that both our delta G, our free energy, and our equilibrium constant both agree with each other. So either the products are favorable or the reactants are favorable. Now we're going to use a equation that we went over before, the KEQ equals e to the power of delta G standard divided by negative RT. We're going to use this equation in order to find our KEQ. We're going to plug in all of our values that we have, so our previous delta G value that we found, the temperature that was provided to us, and our constant value. We're going to plug all that in, and we're going to find that KEQ equals 1.418 times 10 to the 25th. Now, this value is very, very large, clearly very larger than 1. This means that our reaction highly favors the formation of our products. So in the real world, this reaction would actually not be particularly an equilibrium per se, due to the fact that KEQ is so large, but for the sake of theory and for the sake of relating these two together, it is highly favorable towards our products, but some of our reactants are still formed.